Welcome to this video. This video I'm going to be talking about inheritance, virtual functions, and dynamic binding. So before we jump into the C++ definition of inheritance, let me give you a real world parallel. So you inherit traits from your parents, and your parents in turn inherit traits from their parents, your grandparents. So something similar is done in C++. In C++, we have a base class which has properties which are common to all the classes or all the children that might be derived from it. And then you write down derived classes which actually inherit properties from this base class and then add to those properties. They specialize certain characteristics, and those are called derived classes. So I have a class vehicle here, which I'm calling, which is the base class. It's got some properties, chassis number and engine type, which are like common to all vehicles. And then I've also defined a car class here, which I'm saying is publicly derived from the vehicle class. So the class car inherits properties from the vehicle class, and it has its own special set of properties here, or one property to be specific. It has the car type property. So how do you actually, well, let's go into the syntax. You define, how do you define inheritance using these keywords? You have the public keyword, and this is of course the base class from which the car class is deriving from. So this tells the compiler that car is publicly inherited from the vehicle base class. So this is public inheritance. You also have protected and private inheritance, which I'll be covering in the advanced classes. And this you could also have multiple base classes. So you could, it's a comma separated list. You could have multiple base classes. So this is how you would do multiple inheritance. But for this example, I'm going to be using just single inheritance. So it's derived only from the vehicle class. So if you look further down, I've also defined a truck class, which derives from the vehicle class. So this is another derived class. And every class, as you can see, has its own constructor. So you have the base class here, which has its constructor, and the car class has its own constructor here. Similarly, the truck class has its own constructor here. And let me go into the other functions as well. So this is a regular member function, get engine type, and as you can see, it's in the public interface of the base class. So it's also available to the child classes. So get engine type, I'm not actually, if you notice here, I'm not writing a get engine type within car class. That's because the get engine type from the base class is accessible in the car class as well as in the truck class. All right, and there's something new here. Virtual void start vehicle. This tells the compiler that start vehicle is a virtual function. And what does that mean? It just means that this function will be overridden, or it will be specialized in the child classes. So car has its own version of start vehicle, and truck has its own version of start vehicle. So you will have logic which is very specific to a car within this function. I've kept it simple here with just one message, but then you get the drift. It's going to be very specific to truck here. So that's what is meant by the virtual function paradigm. So the virtual keyword tells the compiler that this function is definitely going to be overridden in the child classes. And as you can see, get engine type is not a virtual function. It's just defined only in the base class. And since it's in the public interface, it can also be used by the car and truck classes. Let's now look into the constructor for the car class. So as you can see, the car constructor here takes three parameters: number, E-type, and C-type. So number refers to the chassis number, and E-type refers to the engine type. As you can see here, these are two member variables from the vehicle base class. So the number refers to the chassis number, the E-type, the engine number, and the C-type to the car type. And why has this to be done? Because car is a type of vehicle, and every car object is going to contain a vehicle subobject as well as the car specific subobject. So how do we initialize the vehicle subobject? By calling the vehicle constructor, and that's what is done here. As you can see, the car constructor, in its initialization list, it calls the vehicle constructor, and then it also initializes the variable which is specific to the car class. Car type is a variable, is a member variable specific to the car class. So when this vehicle constructor is called, the vehicle subobject of this car object is getting built. So that's what happens here. And something similar is done with the truck class as well. All right, so within the truck object, you have a vehicle subobject and the object which is specific to the truck, right? So how do we initialize the vehicle subobject? By calling the vehicle constructor. All right, so let's put all this into action and see what happens. So pretty straightforward. I've defined a vehicle object. I'm calling engine type on that object, and defined a car object, and I'm calling engine type and start vehicle. And similarly, truck object, and I'm calling the two functions on that truck object. So let's see how this goes. There's nothing um, special happening here. It's pretty ordinary. Let's see what happens. That's the engine type, and then the start vehicle is called on the vehicle object. The engine type is petrol here, start vehicle on the car object. The engine type is diesel here, and start vehicle is called on the truck object. So that's what we actually did here, and there's nothing uh, remarkable about this. It's pretty straightforward. That's what we expect. But now let's look at, how we can achieve dynamic binding, and how do we actually make good use of this concept of runtime polymorphism. So if you look further down, I have some more code here. Let me comment it out. And yes, so as you can see, I've defined a pointer here of type vehicle. So v pointer, instead of saying v pointer, let me say vh pointer. I think that might. So let me say vh pointer. Right, vh vh. All right. So vehicle pointer here, and I'm initially pointing it to the car object. And so when I call get engine type on vPointer, vPointer actually is pointing to a car object, and it knows that it should, call get engine type on the car object. So it depends on the type of object that is stored in the vPointer. And then I next reinitialize it to point to the truck object, and I call get engine type on the vPointer. Now it knows that it has to call this function on the truck object. So you will remember that get engine type is defined only in the base class. So this is a good example of how inheritance can be used to uh, reuse functions. So we have a function which is defined in the base class, which is common to all the classes. So we are now calling get engine type, which is defined only in the base class, but every time we call it with a different type of object, or the pointer is pointing to a different type of object, and based on the type of object, it will call it will operate on that specific object and get information pertaining to only that object. All right, so that's once again expected. Now let's look at how it works with the virtual function, right? So we have start vehicle here. Now start vehicle, as you know, is has been redefined in all the classes. So it's been overridden. So you have a start vehicle here in the base class, you have a start vehicle in the car class, and you have a start vehicle in the truck class. Now how does the compiler know, which so we are using just vh pointer here, and then once again we are using vh pointer here, and we know vh pointer is just a vehicle pointer. Now, how does the compiler know that it should, call VH pointer, it should call start vehicle on the car object and it should call it on the truck object, because all that the compiler can see is VH pointer. So this is where dynamic binding comes in. VH pointer is bound at only at runtime to the object. So at compile time, it does not know what object is going to be bound to VH pointer. So at runtime, depending on what object VH pointer is pointing to, this function would get called. So if VH pointer is pointing to a car object, start vehicle would be called on the car object. And if VH pointer is pointing to the truck object, so in this case it's pointing to the truck object, so it'll call start vehicle on the truck object. And here it's pointing to the car object, so it will call start vehicle on the car object. So this is dynamic binding. Let's see this in action. So as you can see here, like I said, we have called get engine type on the petrol. Let's look at the last four uh, outputs. All right, so get engine type on the car, so it says petrol. Get engine type on the truck, so it says diesel. And then I'm pointing to the truck object and I'm calling start vehicle, so we see truck start vehicle, and next VH pointer points to the car, and then that's why you see car start vehicle. So this is an example of how dynamic binding works. So we have the same base pointer, but then depending on the type of object that it is pointing to, it calls that specific overridden function. So start vehicle is overridden in each of these child classes. So start vehicle and start vehicle. So this is a very powerful concept and it has to be used very carefully. So we've covered quite a lot here. We've covered inheritance, virtual functions, and dynamic binding. Go over this video lecture a couple of times, and if you have any questions, get back to me. I'll be happy to help. See you in the next video.